I don't know that it's really true that I've been a very active organizer. I think Amit really did all the work, and he deserves a lot of credit for putting all this together. So I thought I would try to give kind of an idea of what sort of data assimilation is about, and also try to give some of the perspective of how we're currently seeing it and where we see the real challenges as being. And it may be that a lot of this is perhaps throwing too much at you too quickly, particularly for the students, but hopefully this is material that will sort of become clearer as it gets filled out by all of the other speakers, the lecturers, as we go along during the week. So let me, oh no, this has stopped working. See it as kind of an issue of our times in a way, because data is coming in abundance, right? Ever-improving experimental technology has led to the situation where there are just vast amounts of data accumulating of all different kinds, from experiments, from observations, from absolutely everywhere you look, there's data. But models are also improving in the sense that the ever-increasing computational capacity has led to increasing amounts of model output and model capability. The resolutions of models are increasing at an extraordinary rate. That means that the computing time to do a given experiment is going down. So that means that the amount of data, if you will, that comes from model output, from computational models, is increasing at a sort of commensurate rate to the rate at which the amount of data is increasing also. Are you going to try to turn this down a little bit? Yeah, it is. It's a bit hot. Okay, so I see it then as a scientific imperative to bring data and computations, that is model output, together to sort of work in harmony, basically to get as much as you possibly can out of both data and models for whatever you want to do, be it prediction, be it estimation of the state, or be it coming back and improving models, which is an important part of data assimilation, that you should use the data to learn about the models and learn what's working and what isn't working. So I just think you just start thinking about it, and it's really a fundamental problem, and it's a fundamental issue that we really should be paying attention to as applied mathematicians and physicists and so on. Well, let me put this in the context of coming to India. So coming to India is a very exciting thing, I think, for me. It's absolutely wonderful, but it's also somewhat scary, right? I mean, you have all kinds of animals here that we don't encounter. Here's one, which I discovered by looking it up on the internet. It's called a wind scorpion. It's also known as a camel spider. And if you look on Wikipedia, it says this. So there are urban legends about these creatures. They're called solifugae, the Latin name, which means flee from the sun. I guess they run away from the sun. And they're the subject of many urban legends, according to Wikipedia. And that they apparently have no venom. Right? They're a sort of a type of spider, but they're distinguished from normal spiders, I guess, with the possible exception of one species in India. Right? So this is scary, which may be venomous, but it doesn't spin webs. And due to their bizarre appearance, many people are startled or even afraid of them. The greatest threat they pose to humans, however, is their defensive bite when handled. There is essentially no chance of death directly caused by the bite. Well, that's sort of encouraging, right? Due to the strong muscles of their, whatever this word is, caliculi, they can produce large, ragged wounds that are prone to infection. So imagine this conversation between myself. Well, these are some more pictures to show you how sort of strange looking these things are. So imagine this conversation I might have with Amit before I come here. I call him up and say, Amit, I've been reading about wind scorpions in India and I'm pretty scared now about coming over to Bangalore. To which he replies, but I've looked them up on Wikipedia and there is nothing to fear. And I say, but it says there is one in India that may be venomous. So I suggest to him, well, let's do this. Could you try to estimate the number of wind scorpions in Bangalore in July, and if it's less than 100 per square kilometer, then I'll come. Okay, this is the deal I would strike with Amit to allay all my fears about coming to India. So what's Amit going to do? Well, what he would do then probably is set up a simple system of two variables, something he could handle as a dynamical system. Let's say he has two variables. One is x1, x2. x1 is the number of male wind scorpions in Bangalore, and x2 is the number of female wind scorpions in Bangalore. Right? You can sort of say every time you look at this, you kind of feel like it's going to crunch you, right? It's sort of awful looking. So perhaps he'd set up a model, right, where you could try to get the state of the system at a certain time, say ti plus 1, from the state of the system at time ti. And I put in here q to denote the fact that this is going to depend on some parameters. So think of q as a bunch of parameters, a, b, c, whatever, that have to take certain numerical values. All right, so Amit's he's going to take up my challenge because he wants me to come to India, right? And he's going to work to produce a model then which will help him predict the number of wind scorpions that are going to be in Bangalore in July, right? So, and he'd do it along this sort of timeline, so he'd take some time t0, maybe that was a year ago or something, I don't know what the life cycle of these wind scorpions is, but and then some time t1, which would be later than that by a certain amount of time, t2, and so on, up to time tn. You know, maybe this is a matter of hours, days, or whatever. This depends on what Amit finds out when he does his modeling of these wind scorpions. But then there are also observations, right? Because you could also go out and try to figure out exactly how many wind scorpions there are. So the observations, I mean, let's say, not quite sure yet exactly what you would observe, but it's going to be some function of x1 and x2, right? So let's leave it at that for the moment. So the point is that if he's going to do this estimate, it would be silly to not use your understanding of the biology of the species to form a model. It would equally be not sensible to avoid using observations which you could go out and get in the field, right? You would want to use both and then try to get the most information you could out of using both of them. Okay, so here's the model again. So what would go into forming the model? Well, I'm not a wildlife ecologist, I'm just hoping that Amit is, right? But I will hypothesize that you might take into account the sort of reproduction of these things, how they reproduce. I looked up on the internet and found enough to realize that there are males and females and there are eggs involved and things like this. So there's obviously the life cycle of these things that's going to be involved. There are environmental factors that would impact how long they live or what might happen to them, interactions with other species. I presume that, you know, you might be tempted to tread on them, or other things might be tempted to eat them, and there's the availability of food, which is presumably other animals for other little insects for them to eat. And then out of that, you'll presumably form a model and somehow set the parameters. Try to sort of judge what the parameters would be from these various different understanding of these different effects, right? So this is what you would do. But there are all kinds of uncertainty in this, right? There's loads of uncertainty in, you know, what the life cycle will be. Have you taken into account all the environmental factors? You can't possibly take into account all the species that these wind scorpions are going to be involved in, that are going to interact with. You probably can't even figure out all the different food sources that they will be able to avail themselves of. There's all kinds of uncertainty in this, right? And that you would call model error, right? So that is your error in the model, right? So Amit is desperately working up this model to try to get this estimate and try to show that in all likelihood there are going to be less than 100 wind scorpions per square kilometer in Bangalore in July. So he's put this model together, but he's got to accept that there's going to be all kinds of errors in that model. There's going to be uncertainty in that model, right? It's just a fact of life. There's no way you can exactly model this situation. And he's also going to go out and get observations, right? So what are the observations? I left it a little ambiguous as to what the observations would be earlier. Just said, well, it's going to be some function of x1 and x2. I'm sort of suggesting here that it's important to separate out the males and the females. And again, I have no idea whether that's correct or not, but it seems sort of plausible that exactly how many there are in the next generation doesn't just depend on the total number, but perhaps on the number of males and females, and there may be different environmental factors affecting how many there are of each of those. But if you take observations, you're probably going to observe only the total number of wind scorpions, right? I mean, if I insist that Amit go out and figure out how many males there are and how many females there are, I think he would legitimately come back and say, but it says on Wikipedia that the only way they can hurt you is a defensive wind bite. So if I'm picking these things up and trying to figure out whether it's a male or a female wind scorpion, I think that's going too far. Right? So he can probably only observe the total number. So that means the observation is probably the sum of these two things, right? So that seems sort of perfectly reasonable, but you're not getting a total observation here of them individually. So that's an important point. Right, well, it's also true that Amit would say, well, look, what do you expect me to do? To go around Bangalore and count all the wind scorpions in Bangalore? So I think that agree that that would not be reasonable, that he would really do it in a restricted region. So let's look at some restricted region here. Oh, somehow I've lost the internet. Oh no, I thought, darn, oh, it went off. All right, well, maybe it should come back on. It should connect me. Sorry, I didn't think about that. Yeah, there we are. Okay, so here I set up a map in Google here, which should show me my places here. TIFR, so we'll choose somewhere for Amit close to TIFR. Okay, so this is TIFR on Google Maps. Okay, so what I thought was reasonable to get Amit to do was to perhaps check the area here between TIFR and the Mandara hostel, right? So there's this sort of open area here, and I thought it was kind of reasonable to suggest that once every day he'd go out and count the wind scorpions in the area between TIFR and the Mandara the hostel, okay? So that would be the task. Now then, obviously that's, again, going to be somewhat inaccurate, right? Because there's going to be lots of issues with him missing them. They might fly off as he tries to see where they are, and all kinds of issues like that. But it's also, you're only taking a restricted region here and somehow extrapolating to all of Bangalore. There's no reason why the density of wind scorpions in this area should be the same as the rest of Bangalore. But you would have to presumably make that hypothesis if you were going to do. Oh, I'm sorry. Now I've got all my Skype mates coming up. Right. Sorry, I'll turn the radio off. I don't need it anymore. So you would want to extrapolate to all of Bangalore. So there's all kinds of error in doing that, right? Because there's no reason to believe it's going to be the same density elsewhere. So again, there's all kinds of uncertainty coming up, right? This you would call observational error. Right? There's the human error of Amit going out and counting these things, but then there's also the sort of error in the whole setup of the thing, how you're concluding the actual data that you want from the observations that you're taking. Okay? So there's lots of observational error. So you have to face the fact that there are these two things. You can put a model together, and this is where you put your a priori understanding of the world, the physics, the biology of whatever, into the model, and you can go out and make observations, but there's going to be errors in both. So how does data assimilation work? It deals exactly with this situation, where you have observations and you have model output, but they both have some uncertainty, and you want to get the best out of it as you possibly can. So what I want to do is kind of give an overview of the techniques that are available for doing that and the different ways of looking at it. So let's take our two variable system of males and female wind scorpions in Bangalore, and let's assume that the upper T here means truth. Right? This is time and this is truth. It's a slightly different font. And it's unfortunate here that in the area of data assimilation, T is used for truth and we use it for time too, but that's something you have to get comfortable with. The triangle here is going to always be truth. So we're interested in, say, you remember Ahmed had the problem of starting at time. I hope you don't mind me referring to you all the time as my sort of stand-in person who's doing things. So starting at time t0, you want to go to time t1, right? Because he wants to figure out the number of males and females of these wind scorpions at time t1, right? So the real world provides some really sort of jagged trajectory and some perhaps, pretty sort of unpredictable and difficult path to take you to some value at time t1. Now you're going to model this, so you're going to make some guess as to the state of the system at time t0. Right? So you've obviously got to start somewhere. So maybe he looks at historical records of numbers of wind scorpions in Bangalore, some kind of estimate, right? And uses that as a start and puts it into the model. Well, you're also going to think about some kind of confidence in that. So the confidence in this is where the uncertainty comes in. I will normally denote by the letter uppercase P. Right? So you've got a guessed state of the system and you've got some confidence in that. Think of it as a normal distribution based around this as the mean and this perhaps representing the variance. Okay? Now then, you've got a model which will take this and go forward and forecast what the value will be like. That's this upper F here. That's the forecast. Actually, we use F for the forecast of the initial condition. You might call it a nowcast, right? But it's actually in the same qualitative sense as you're forecasting the thing because you're sort of guessing what it is. And you know there's some error. You also want to evolve your confidence in this in terms of this variance, or this covariance, right? And so think of this as a variance around this sort of mean. How you get this object here really lies at the heart of data assimilation, because this is your sort of uncertainty somehow of the model, right? Of what the model has done and also your initial guess. This is sort of lumping together a bunch of uncertainty. Now you're also, though, going to take a measurement. So we've said that Amit is allowed to actually go out and count the total number of wind scorpions out there. And that's going to be a measurement, right? But there's going to be some error in that. So let's add some epsilon to say there's some kind of error bar around that counting, which is the observational error. So now you have this situation. You have this model forecast, and you have your measurement, and you want to somehow come up with a better guess at the state of the system, of the number of X1s and X2s of these male and female wind scorpions at time t1, given this information. Okay, so that's called the state estimate here, and you usually use this uppercase, this superscript A, which means analysis. It stands for analysis because that's after you've analyzed the problem. And you also want to be able to express some confidence in that, right? So somehow out of this stuff and the epsilon, the PF, this stuff, you want to get a good estimate here and a confidence in that. Okay? Well, the standard way of doing that, and I think this is probably, applied mathematicians, this would be the first thing you'd think of and say, well, let's take our forecast And then let's take the difference between our measurement and what our forecast says the measurement would have been. Remember, this is the operator that takes us from state space to observation space. That's what this H observation operator is. So you'd want to take some sort of, kind of linear interpolation between this forecast here, so xf is this 2 vector, and this thing here, which is the difference between the measurement and what the measurement would have been had this been correct. Right? I mean, you've got 2 points, right? You've got your guess here from the model, and you've got your observation. You draw a straight line between them, right? And you'd say, well, let's choose somewhere on that straight line between them and say that's the better guess. Where you go on that straight line between them would depend on your confidence in the 2 things, right? Now, the only thing is that the dimensions don't add up here, because this is actually 1-dimensional and this is 2-dimensional. This is a 2 vector and this is a scalar. Well, that just means that K is not a square matrix. Okay? So K is called the gain matrix. Right? So this is a very natural thing to do, this kind of interpolation strategy. So sequential data assimilation, remember Amit can't just get away with one time step. He's going to guess the number of male and female wind scorpions sometime in the past, or look it up in some book of historical numbers of these things in Bangalore. And then he's got to progress using the model through time and use the observations that he's made when they're available. Right? So he's not just doing one time step, he's doing it repeatedly. So that's called sequential data assimilation. You got the model, the observations, and you want to get some kind of prediction, because he's trying to predict what it's going to be like in July. This is before I came here, right? So he starts at t0, he goes to time, applies the model, goes to time t1, and then he makes the observations, he does this interpolation, he updates, and he starts again. Then he applies the model again to time t2 and goes through that operation again, and then so on up to time tn. Just keeps repeating this at each time step. What I described for you in the diagram before is what happens in one time step, but he just keeps repeating it. This is sequential data assimilation. Okay, this is let's go to a slightly more complicated thing. And apply this sort of scheme of sequential data assimilation and think how it might work in something more complicated. This is the Gulf of Mexico. In some sense, this is like our version of our being American version of I suppose, what do you call the Indian Ocean off of the west coast of India? That's just the Indian Ocean. The what? Arabian Sea. Arabian Sea. Okay, so this is, in a sense, to us what the Arabian Sea is to you. We're really interested in the Arabian Sea because that's where the monsoons come from, right? Because that produces the monsoons. And the Gulf of Mexico is very critical to us because of what it does to hurricanes that go across the Gulf. This was an article in the New York Times shortly in 2005, shortly after Hurricane Katrina, and the one that's a little less famous, but in some ways was just as strong, Hurricane Rita, which came a few days or a few weeks later and hit Texas. But this did not have the dramatic damage that Katrina did. And one might ask, actually, why Katrina was so bad. I remember the weekend before Katrina, I was actually supposed to go to a conference at the Navy Research Lab in Stennis the day that Katrina hit. And luckily this was a conference on data assimilation, and the people who were running it were extremely smart, and they looked at the news on Saturday, which actually was rather ambiguous. It came through on a Monday, the day the conference was going to start, and they called it off, which was very thankful, for which I was extremely thankful, because we might have just got in and we would have been stuck in the whole mess. It would have been a complete nightmare. In fact, I was watching CNN the night of Hurricane Katrina, and the woman who owned the guest house where I would have been staying was walking along the beach and got interviewed by one of the news reporters, and she said, "I used to have a guest house here," and you could see there was nothing there, and this was the day after I was supposed to be there. Anyway, everyone has their own personal stories, and obviously there are many that are really awful, but you can see what I remember the weekend before, though. Hurricane Katrina was being sort of written off. It was a Category 1 storm hitting Florida, and it gathered extraordinary strength as it went through the Gulf of Mexico. Why it did was because it passed over some very warm core loop loop current rings, they're called, which are big eddies in the Gulf of Mexico, which spin off of the loop current, which is really a part of the whole Gulf Stream complex, bringing the tropical waters up to across the North Atlantic. And it was the heat source of these that energized Hurricane Katrina and turned it from a Category 1 into a Category 5. A similar thing happened to Rita, but you can see it didn't get quite as strong. It's the width of this band that indicates category hurricane strength. You can see that this isn't quite as red as this bit here. This is a sort of three-dimensional picture, so actually this is right over here. It passed right over because it went into the middle of the Gulf and then took a turn. This did not pass over, so it wasn't quite as strong, Rita, which was one reason it wasn't as quite as damaging. But anyway, this is one of the points I wanted to make here is that this is a model which is run continuously by the U.S. Navy called Nonlinear. This is from 2005, but a few months later, this is September, you can sort of see the dates running through here. And the point is, though, when you see pictures like this, you're sometimes led to believe that they're satellite pictures, and they're pictures of sea surface temperature, sea surface height, which are very closely related to each other, but you're looking at them from satellite. The fact is, though, that they're data assimilated model pictures. In other words, you're using the data from the satellites, but that is not enough to give a picture like this. So they're running models of the Gulf of Mexico, in fact, global. This is the naval layered ocean model, and it has 1/16 of a degree resolution, and they're running these global models and assimilating that kind of satellite data into it. So this is a product of data assimilation. So how would it go in an ocean model? So this is sort of a generalization of what I was saying before with the two-variable system. You now want to think of a much, much higher dimensional system, right? So X in general would be in Rn. So how would you put this vector together when you're doing data assimilation? Well, this is actually a piece of the Gulf of Mexico here, and this is from a model of some work I was involved in, but this just sort of a piece extracted. This is actually a little bit of Cuba. This is the loop current here. What's being shown is velocity field, so you can see the strength of the current. This is an eddy that has spun off, going around this way. And what you're seeing here is grid points from the numerical computation of the top layer of this computational model, and you're seeing the velocity vectors at each of those grid points. So your state space would be take each of these grid points and take each of the physical variables in the model at those grid points and string them along, right? So you take, flow velocity, the two different horizontal velocities, vertical velocity, temperature, salinity, pressure, whatever's in your model, right? And you would just sort of list those variables, the 5 variables for this point, 5 variables for this point, and so on, and build up a very big vector, right? So just a much more complicated form of my x1 and x2 that I had for the model of wind, the hypothesized model of wind scorpions. You would then have a model, right, which would tell you really how to move the state of the system forward in time given a certain time step, right? It's sort of represented usually in this kind of differential form because we're about to write a stochastic equation. And this model would come from solving some partial differential equation, which would probably be the primitive equations of geophysical fluid dynamics, which are simplified versions of Navier-Stokes. The actual evolution would be some stochastic perturbation of that, some random perturbation, so some unknown realization of a stochastic perturbation of it. That would be the true system, right? Our model is deterministic, and our truth is somewhat unknown, so we think of it, well, it is unknown, so we think of it as a stochastic perturbation of that. And this really encodes the model error, right? Because it's the error that the model has. And we assume that that maybe has some simple statistics. It's delta correlated, so that's the covariance. But then we also have observations. Now, a key thing here is that, and I said this in the case of this two-variable model, that your observation space is probably not the same dimension. It's probably a lower dimensional, right? You observe less than you can actually compute in the model. The computations are still so important. Well, so this is your observation operator here with some error, and then that is going to belong to some RL, but typically that would be much, much less than N. That's certainly true for ocean models, which is what we've been involved in. So, and then you assume that that has the statistics here are correlated in some way. So imagine that, you had sort of moorings at 4 different places in the ocean, and this is where you could make your observations. Okay? Well, obviously, whatever you observe there, temperature, salinity, or whatever, is obviously going to give you, 4 times 2 or whatever, 8 variables, and that's going to be far, far less than your full Rn. There's no way you could observe the thing at every grid point. Temperature and salinity. That would be crazy to even suppose that. It's also true there's no reason to believe that these points should be at grid points of the computational grid, so there may be some linear interpolation in this H here. So this is not a simple projection necessarily. If these are maybe not variables that actually appear on the list here, this could then be a more complicated operator, perhaps even a nonlinear operator. Right? So there's no reason really a priori to assume that this H is linear. In the simplest form, it might be a projection, or it might be some kind of linear thing if it's a linear interpolation, but it could be more complicated. All right, so let's summarize the whole thing again and introduce some notation. So we've got a state of the system here that's in Rn. All right, I'm going to sort of drop the T sub I and all the multiple subscripts and just talk about X sub I plus 1. And that's now, the model tells us how to get from Xi to Xi plus 1. And that depends on some parameters. All right, so sorry, my notation here is bad, and this is now does not mean x1 and x2 as individual components of the vector, but denotes the state of the system x at some time ti. Okay, and you're moving them, progressing under the model from some starting time to some ending time. And you have observations of these, right? So you have some y0 and some observation of the true version of x0. y1 is an observation of the true version of x1, and so on. These are supposed to be little telescopes, you see, so that's why the observation. And then you have this observation operator, which takes you from Rn to Rm. And those are the observations. And what you're observing here then is this sort of version, this kind of truth here, which these are modeling and these are observing. Okay, so that's sort of like sitting in the background is the true world, and you're modeling it and observing it, and you want to put these things together to get the most information out of this that you can, the best estimates of the state, the best predictions, and so on. So what are the typical problems, right? So I'm going to sort of ramp up now and explain in a way where that guessed at formula came from, and what the gain matrix should be, and but I'm going to do it by looking at this as a variational problem. So I'm going to sort of switch the perspective a little bit. Instead of saying, well, it's obviously some kind of a point on a line between your observation and your model output, I'm going to think of it in terms of a variational problem. But it's useful to think about what are the actual problems that you think about. One is to estimate the state at the current time, right? And in a way, that's kind of the basis of the prediction problem, because you get your best estimate of the state of the current time, you can use the model to predict. So that's related to the prediction problem. You can't really use it, it's a data assimilation can't really be used to improve predictions per se, because you can't get any data in the future, right? What you really do is improve your estimate of the current state of the system to plug into the model, okay? The other thing we often do is estimate the initial conditions, right? So you kind of like take some data, afterwards, and you go back and try to get a better estimate of the initial conditions, right? That's a related problem. Another problem is to estimate parameters in a model. All right, let me take the estimating the state at the current time. This is the sort of predictive mode, the sequential DA, as I described it already, and is known in the statistical literature as filtering. So here what you do is you minimize this cost function. Okay, so this is another way of putting it. Instead of doing a sort of linear interpolation between these two things, what you say is you form a cost function here, right, and you try to minimize it. Well, there are two pieces to this cost function. One piece is related to your sort of prior estimate, right, what your guess is or what your result is from the previous steps that you've done. And the other is your observations. And somehow what you're going to do is you're going to sort of add these two pieces together, right? One of which is sort of representing, would be sort of minimized by your exact model output if that was the only thing around, and the other one would be minimized by your exact observations if that were the only thing around. But then you add these two things together and you say, how do they balance out? And think of them each as quadratics, okay? I'm going to comment on that in a minute. But think of them as adding two sort of quadratics, then the spread of these quadratics will sort of tell you which one of these is somehow weighing more than the other, or the relative weights of these two pieces, right? So, I'm using the notation P here, so you know that that's the thing which expresses the confidence in the model. This is the thing that expresses the confidence in your observations. So this is called the background error covariance. Sorry, that should say P sub I. This is at time I, and this is the observational error covariance, right? So you come up with some guess, which is your xi, right? And you're going to sort of improve that to move towards the next step, right? And what you want to do is improve it in light of the fact that you've gotten these yi's here. But you've got to have some confidence, which is your observational error covariance in that. So that forms this kind of quadratic form. And then you've also got to think about what's your confidence in your guess up to that point. That's sometimes called the background error covariance. Okay? And you say, well, what you should do is you should minimize that guy. Now, variational data assimilation is somewhat contrasted with that, and this relates to problem 2 here, this estimating the initial condition. I won't address the parameter estimation directly. You can imagine how it might go, but so in this case, it's called the reanalysis mode rather than predictive mode. So you're sort of using data and going back and reassessing your starting point. In the statistical literature, it's called smoothing. So here you might minimize this cost function. Okay, this looks a little more complicated, but when you start to unpack it, it isn't that much more. Again, there are two pieces. The first piece here relates to your sort of guess of the initial condition, and the second piece here relates to your observations in the various times after the initial conditions. Things don't break quite so cleanly in this case here, because you see there's no real sort of model occurring here, because you're not evolving a model, and that's actually hidden in the H here, because you're evolving the model and then observing. So it's sort of hidden in your observation operator here. So it's a little bit more complicated. But you're summing here over a certain index set here, which relates to the fact that you start at a certain point, you move forward, and you do observations at various time steps after that. Okay, so, but again, you weigh your observations and you weigh your sort of prior guess here. So again, this is called the background error covariance. This is the jth observational error covariance, and this is your initial guess. So your initial condition estimate is x0 star. And then you want to minimize this cost function. Again, you're sort of weighing two things, right? Okay. So how does the interpolation and the gain matrix come out of this? Well, if H is linear, or linearized in some way, if you linearize it in some natural way, then this exactly is a least squares problem. This is quadratic, right? And the solution is then found by that sort of interpolation, right? This is a calculation. You can see that. And the gain matrix is given by this formula here. Okay, so it's pi h transpose blah blah blah, right? So you can calculate what k is, and this object here, xi, minimizes this cost function. Okay, so if everything is linear, right, then you can actually calculate it, and you get this gain matrix out. So that's how that relates to the cost function approach, the variational sort of view of this. So do you linearize or do you not linearize? This is a fundamental question in data assimilation, and this is something that I think should be kind of an organizing question here. Well, this sort of really only works if you do linearize, but it gives this nice sort of formula here. And let's look at sort of situations where you really got to, what we got to figure out here, the only thing that's kind of unknown in this is the pi. Right? The h has to be linear. That's going to be my hypothesis here, and then I'm going to explain sort of what the shortcomings of that are. Right? But the big question is, how do you get this p? So the r is the observational error covariance. So you somehow decide that ahead of time. I'm going to decide what kind of confidence I have in Amit going around every evening and counting the number of wind scorpions between here and the hostel. And I know that some evenings he's going to go out there and he's going to say, this is absolutely ridiculous. I'm getting pissed off from doing this, and I'm going to actually go home and play with my kids, and I'm not going to count any more wind scorpions. So I got to take that into account when I form this R here. But that's kind of some kind of a priori thing, right? You decide ahead of time what that is. But the PI is somewhat more complicated because it's sort of accumulating errors maybe from your models and stuff like that. So, but how do you figure out what it is? Well, you could take it to be a constant, right? You could do the same as we do for the observation. You could say, I have this level of belief in my model, and so I'm going to use that level of belief, encode it in some error covariance matrix, and stick with that forever. That's called optimal interpolation, or OI. Another thing you could do is, if the model is linear, you can evolve the PI under the model. You can say initially, right, so think here of the sequential data assimilation. That's the framework we're working in here. Right? Initially, you take some initial confidence in it, and you then evolve that to your confidence in the next stage. You could use the model to evolve that if it's linear. That's exactly what the Kalman filter does. So you will hear about the Kalman filter during the week a lot, and that's what the Kalman filter does. It comes from linear control theory. Kalman was a control theorist, and this is sort of the natural formulation of this problem. However, it assumes that the model is linear. If the model is nonlinear, what you can do is you can evolve it under the tangent linear model. That's to say, what you do is you think of it as going a model trajectory moving along, right? You think of this as a dynamical system. You've got a model trajectory moving along without doing any data assimilation. Okay, so you want to think of it just between two time steps, for instance. And along that trajectory, you linearize the nonlinear model. Right? So then you've got a linear model, which is the linearized version of the model along the trajectory. Right? That's called the extended Kalman filter. In theory, that could work very well, provided you're looking sort of somewhat locally near the model trajectory and your errors aren't too large. This can work very well, but it's computationally quite prohibitive because it involves these incredible linear algebra, these large matrix calculations, right? But then there's a modern method of this, which is really quite interesting. It's quite interesting in its conception mathematically, and it's also quite interesting in the way it works. This is called the Ensemble Kalman filter. So what you do is you build the PI out of some ensemble. So you make a spray of around the initial conditions and say this spray represents, possible other estimates. And in fact, if you force me to give a best guess, what I'll do is I'll just say take the mean of that spray as a distribution, all right? And then evolve that whole spray, but evolve it under the nonlinear model. Don't linearize. But then when you're done with that, try to find the best sort of linear approximation to that, which in this case means find the mean and the covariance of that spray, that ensemble. And then you can use that. I'll explain that a little bit more in a second. The fact remains that for large models, linearization at some level is necessary. If you've got any operational weather center, any operational data assimilation system, right? If there is, if they're large, that's to say, you're looking at state spaces of the order of 1 million or so, then linearization is inevitable, right? It's just a part of the game at this point. And this is in a way the grand challenge of data assimilation. And I'll talk about that again in a minute too. This is how the Ensemble Kalman filter works. So you take a spray of initial conditions. This is in the framework of our x1, x2. Unfortunately, I'm sorry, I took the notation changed slightly to xy from x1, x2, but it's the same thing. This is our truth and this is our model guess. But instead of evolving just one guess, you evolve all of these guesses under the nonlinear thing. Right? Again, your guess here at time t0 is actually just the mean, the average of this spray of initial conditions. And your model forecast is the average of the spray of these things here. But you also want a confidence in that, right? A covariance. You need that to do the sort of Kalman type, Kalman gain update, right? So this is the same matrix formula works. The question is, what's your PF? Well, you form your PF as a covariance matrix, right? Just in the natural way, using that ensemble, right? That's the basic step of the Ensemble Kalman filter. Okay, but what if linearizing throws away too much information? For instance, the observation operator H may be nonlinear, right? This could be a nonlinear operator. As I said that in the beginning, it's not necessary that H be actually linear, right? So it could be nonlinear. So this is an extraordinary challenge, really, to try to understand how to do this. This then ceases to be quadratic, most likely. J is not necessarily quadratic. So this is now much more complicated. So for instance, you're not guaranteed that there's a unique global minimizer anymore. So you may now need to find a global minimizer in the presence of possibly many local minimizers, right? So you do some minimization strategy, and you may well find a local minimum. It may not necessarily be a global minimum, right? So even if we do find a global minimizer, you might legitimately ask the question, well, is that really what you want? This is a picture of a cost function that comes up in calculating the Lorentz equations, right? So the Lorentz equations, the Lorentz 63 equations that Lorentz, right, are the equations where the term was coined about if a butterfly flaps its wings in Brazil or whatever, you get a tornado in Beijing or something, then those equations for modeling convection, those 3 variable equations of Lorentz, if you try to calculate a cost function in that under certain conditions, and this was done by Jochen Voss, who was a collaborator of Amit's and mine, you get something like this, right? So you might say, well, okay, if I try to find a global minimizer of that, I mean, there are some candidates down here, but you might also question what's the value of that information given the structure of this cost function, right? So it's clear that you need to learn more about the cost function. Let's turn to how statisticians would think about this problem. Right? So I've given you kind of an applied mathematician's point of view so far. It's an optimization problem. It's a variational problem. You use, you work out some formula using a gain matrix that tells you what the best answer is. Well, a statistician, I think, would look at this, or they do look at this and say, well, you can't really just have one single answer here. There is no one single answer. In fact, there's a whole probability distribution of answers, of estimates. And it comes from Bayes' theorem. Bayes' theorem is the theorem is basically the law of conditional probabilities. And it tells you that the probability of the state of the system X, given the observations Y, is proportional to the probability that the observations occur given the state of the system, that's called the likelihood, times the prior probability that the state of the system occurs. All right, so in other words, the statistician looks at this and says you shouldn't be just looking for a single answer. I could have told you that you would have problems with that, like you do in the Lorentz equations. You should be looking for a probability distribution. That's Bayes' formula, right? So the Bayesian view of sequential data assimilation is then the same, except that Bayes' formula replaces that interpolation formula. And that's given by this, as I said before. This is proportional to this. But really, actually, for a probability distribution, proportional is really everything you need, right? Because you just scale this so as the integral is 1, right? So it's a probability measure. But scaling something, right, the structure of the thing doesn't change where you multiply by a scalar. The maxima are still the same and so on. Okay, so a key question then is how do we actually obtain these distributions? Bayes' formula actually in theory gives you a sort of kind of a global answer to the data assimilation problem, but to think that the data assimilation problem is then solved is like thinking that the problems of fluid mechanics were solved when the Navier-Stokes equations are written down, right? This is really just the beginning of the story. So in principle, you should be able to evolve these PDFs. This is analogous to finding our PIs, trying to find these PDFs. Right? If you applied this in sequential data assimilation, then this is the prior. So this would be your, say at time t2, this would be your probability here that the state of the system is something. Right? And then you would be including the observations here in Bayes' formula to get a posterior probability. That's after you've done the step. How do you get this sort of prior here? Well, you would get the prior by evolving from whatever posterior distribution you had at the previous time step. Right? And the way you do that is the Fokker-Planck equation. Right? This is a picture that shows how that would work in the two-variable system. Okay, this is and I know I'm throwing at you rather a complicated PDE, but I'm going to tell you in a second that it's hopeless, so it doesn't matter anyway. So how do you evolve probability distributions under models? You evolve them according to the Fokker-Planck equation. This is actually the errors, if you remember notation I had a number of slides ago. This encodes the model error, and this is how the model works itself. So, but the picture is the following. This is again our two-variable system here. You've got some PDF around your initial guess here, and you evolve that under the model, and you get some new PDF. Right? That's exactly what I said. If you had a linear problem, then the Kalman filter, right? That Kalman's approach is to say evolve your covariance under the linearized problem, so now I'm evolving a whole PDF, and I'm drawing it like it's a Gaussian, but it may not be for this, for purposes of this. Now then, the Bayes step here, or the update or analysis step, is now you've got a measurement, remember, of one of the variables. Well, actually, I got a measurement of the sum, right? But if I think of it as a measurement of one of the variables here, this is a PDF on one variable. I've got to take that, multiply it by this, and get a new PDF. And that's the Bayes step. I mean, that looks absolutely perfect. It's absolutely wonderful, right? You just do all these probability distributions, evolve them under this PDE. But this is computationally prohibitive, because the number of independent variables here is the number of state variables in the system. And for things like atmospheric and ocean models, that would be the order of 10 to the 6 or more. Next generation will be 10 to the 7, 10 to the 8, and so on. Right? 1 million, 10 million, 100 million. So computing this in dimensions, independent space dimensions 2 or 3 is quite difficult already. So 10 to the 6 is way beyond anything any computer can do. Let's talk a little bit about variational data assimilation, right, as opposed to the sequential data assimilation. Right? I'm throwing out all of the problems here, and I'm going to weave them back together. But again, this is an overview and an introduction, so I'm not solving all the problems here by any means. So here you take model runs and observations and come up with a state estimate. Remember, this is where we'd be trying to estimate the initial condition. Start at x0, apply the model, go to time t1, t2, t3, up to time tn. You've got x of tn. But what you want to do is estimate the initial condition x0, given what happens later. Well, what do you know about what happens later? You know what the model tells you, but you're also going to have some observations at each of these time steps, right? If you do this from the Bayesian point of view, then you want the posterior of the x, which would actually be our x0, our initial condition here, given the observations of what comes out of that x0, is equal to, sorry, this should say proportional to, the observational likelihood that the observations happen given the state of the system times the prior. Well, that's all well and good, but this is what you'd have to do if you actually wanted to get these distributions. The natural way to do that is to just try to do lots of realizations of it, right? Build up a sort of histogram and try to sort of estimate the PDF. Right, so you sample the posterior. Well, that means doing loads and loads of model runs, right? Well, your friends at the Weather Center are going to get very irritated by this, because they're going to say, well, look, it takes us, we try to do one model run to get an estimate, and you're asking us probably to do thousands of model runs. We can't possibly do it, right? It's crazy, right? So that's sort of a problem. But Bayes' theorem really helps you if you are in the nonlinear case. So if it's not, it gives you really a general way to look at it, and that's the great advantage of looking at it from the Bayesian point of view. So it gives us a way to look at the full nonlinear problem. So that's exactly what the PDF is. It's the exponential of minus the cost function. That means that the mode of this distribution is the global minimizer. Right? So your variational problem is exactly actually equivalent to finding the mode of the PDF. Okay? We discussed this in a paper, Amit and myself and Andrew Stewart and Joachim Voss, who I mentioned earlier, in a paper in 2008. So if this is our J here, this is from our variational DA problem, then the claim is that the posterior here is actually the exponential of minus this cost function. All right, now think about this for a minute, and you'll see it all falls out kind of naturally, because suppose I take the exponential of this, and forget the minus sign for the moment. Right? I take the exponential of this thing here, then that's the exponential of this, right, times the exponential of this, right? Well, the exponential of this is exactly your prior probability, right? Because that would be, and say it would be the exponential of minus of this, that would be your prior probability of the initial condition. And the exponential of this bit is exactly your observational likelihood. right? So you see how sort of Bayes' theorem, once you sort of realize this, Bayes' theorem is exactly the statement that you're adding these two pieces in the cost function and trying to balance them out, okay? So in a sense, what the statisticians are saying is they're saying that you shouldn't just be looking for the global minimizer of your cost function, you should actually be looking for the entire structure of the cost function. So let's talk about nonlinearity versus dimension just for a moment. So this really is the big sort of elephant in the room, is the fact that we can deal with nonlinearity in low dimensional problems, right? But once you go to high dimensional problems, basically any solution strategy has to involve some level of linearization. Right? So that's, and the most sophisticated is perhaps the Ensemble Kalman filter, but still, even though you evolve the spray under the full nonlinear model, you still put a linear Gaussian sort of straitjacket on it at the end of the day. All right, so if this is the cost function here for the sort of variational DA problem, right, and the posterior PDF is proportional to the exponential of that. The question is, what are the strategies we have for getting a hold of this posterior distribution? Well, these are called sampling strategies. One is particle filtering. Another is Langevin sampling. That's something that Amit and I learned from Andrew Stewart and started using, but actually realized that it was not as effective as Metropolis Hastings, right? I think that's fair to say. That was the conclusion of one of our pieces of work. And then you can also think about importance sampling, which is another sort of strategy for if you have a priori information about some a priori information about a PDF, then you can use that information to focus on what you think are, or what you know are, the important parts of the distribution. And you can bias towards that to get a hold of it. And this is something that Elaine Spiller has worked on. And I guess Elaine will probably talk about some of these strategies here later in the week from the sort of, for the Bayesian part of this. But the problem is none of these are well developed in high dimensional problems. Elaine Spiller, who's talking later in the week, who's giving one of the main series of lectures, and I worked with Kayo Ide and Amajit Budiraja, who's a statistician, well, really a probabilist at North Carolina. And we were working on this sort of low-dimensional problem that came up in Lagrangian data assimilation, which is something we've all been very interested in. And maybe something you'll hear more about, I don't know, but it doesn't really matter, except that the problems we were looking at were quite low-dimensional. And we wanted to increase the dimension of it. I don't know if you remember that day in my office when we asked Amajit, well, could we go to the slightly higher dimensional problem? And that would be kind of 15-dimensional, right? Something like that. And Amajit just suddenly, when he's not a serious guy, he's a very bubbly sort of person, but suddenly he looked glum and he said, but we can't do anything more than 5 dimensions. And you want to do, for ocean and atmosphere, you want to do 1 million dimensions, right? So so we've got this kind of theoretical answer to the data assimilation problem in terms of these probability distribution functions, in terms of Bayes' theorem and so on, but you've got this extraordinary challenge that really the techniques for effectively and confidently sampling the PDFs to the point that you know that your sampling is converging to the probability distribution function are really, you can only confidently use in low-dimensional problems. Let me just finish by trying to sort of chart this all together and sort of put it together and try to give a sort of balance, right? This program course, Monsoon School, that's what we call it, right? The Monsoon School is devoted to the mathematical and statistical foundations of data assimilation, okay? So this is something that I think a lot of us kind of have grown to believe in, that the statistical point of view is tremendously important, and that is that taking this sort of Bayesian perspective is the right way to sort of look at the whole problem. However, if you come back and look at it as an applied mathematician, what you're doing there, you can actually see it the same way. So you can see this rather nice equivalence. But let's look at the different sort of points of view and where they have carried us and what the sort of balance is. So this is the applied mathematician's point of view, is to say, think of it as an optimization problem, right? You want to find the best estimate. Right? The statistician's point of view says, no, you want to think of it as a conditional probability problem, right? You've got observations, you want to find a probability distribution of the state of the system given those observations. That's a conditional probability. The optimization point of view says, well, you formulate it as a variational problem, right? You want to minimize some quantity, so you get the quantity and so on, and you think about how to do that from a variational point of view. Conditional probability is Bayes' theorem. In the variational formulation, the key object is the cost function, right? You're going to look at a minimization of a cost function. Your cost function is going to encode everything about the problem. From the Bayes' theorem point of view, the thing you're after is the posterior PDF, right? That's the thing that you want, right? You want to get the posterior PDF. But as I pointed out, these two things are actually completely equivalent. They're just related by the exponential function or the log function, right? So this is the exponential of this is the log of this, with a minus sign in there, right? Other than that, and some scalar multiple. But as I say, that doesn't really matter when you think about the structure of this thing. That only just sort of increases it, decreases it. Doesn't change any of the places where the minimizers and so on occur. If you look at it this way, you want the posterior mode. That's the first piece, the primary piece of information. Over here, the primary piece of information is the global minimizer. And these two things are then equivalent. In fact, they're exactly the same. Where you get the global minimizer is where you get the posterior mode. Now, what are the temptations on these two sides here, right? This is actually a complete nonlinear formulation, and these two things are exactly equivalent, right? When you come down to it at the end of the day. This is driven by a point of view of looking for the best estimate, and this is driven by a point of view of looking for a probability distribution. But at the end of the day, these are completely equivalent. But the temptation over here is to look for a normal approximation, because PDFs in general are too difficult to deal with. So the temptation is to look for Gaussian PDFs, which we know are determined just by their mean and their variance. And for Gaussians, the mean is the same as the mode. Right? The temptation over here is to get your cost function into a least squares problem, to make your cost function quadratic. That's equivalent to linearizing the problem, to linearizing the model and the observational model. But these temptations are exactly the same on both sides, right? They're exactly equivalent. The minimum is going to be the mean, and the only other piece of information about a quadratic cost function is its spread, right? Right. So the spread is equivalent to the variance. Right? Or higher dimensions, spread in different directions, and covariance, and so on. So this is, in a way, the sort of situation, really, of this is kind of really well studied, and this is really well known, and forms the kind of the basis of what we do in data assimilation and what's done operationally in data assimilation. So I've got a line along here, too, between the known and the challenge. So what I claim is the challenge is what forms below this line. But again, there are complete analogs over here and over here. Over here, you want to look for the full structure of the cost function. Look for minimizers, critical points, and so on. Over here, you want to look for the full structure of the PDF. Higher moments, maxima, regions of high probability, stuff like that. Here and if you think about it, it's the calculus of variations. The calculus of variations has not restricted itself to looking for global minimizers. There's a lot of work on finding other critical points and looking at Morse indices and so on. Over here, it's the sampling strategies. But again, if you look at it in its full generality, these two points of view are actually equivalent. It's just that in the first place, the search for the best answer drove it in kind of a different direction, but it was equivalent to this once the probabilist restricted to Gaussians. It was actually equivalent, right? So you've got equivalence all the way up and down in the end. So the statisticians and applied mathematicians' point of view, in a way, come back together. So that's my sort of chart to kind of summarize everything. I know for the students, I've thrown a lot out at you in these different pieces. We don't expect you to have understood at this stage at all. But I hope as you learn during the next 2 weeks, you can come back and look at this and say, oh yeah, that's what he was talking about. That's what he was talking about. So, okay, that's it. I think I've taken my time up.
But don't ask me about the wind scorpions. Anything else?
Okay, the variational formulation when you do, what you are taking is, you have obtained, your model predicts something.
Right.
And are you assuming that the prediction which comes out of the model is a minimizer of some variational problem associated with this, independently?
Well, it could be, yeah. I mean, it could be. I mean, that seems like an interesting situation to think about, actually.
See, because if you are minimizing both,
right,
okay, at the same time, that's what your model does. You put in both the data and you minimize because.
Yeah.
Supposing what you have obtained here is
right.
a minimizer,
right,
but
right.
what you have observed is not really a
right,
minimizer.
right.
How does this?
Yeah, well, I think that's actually, I mean, one reason I wanted to, there were a few reasons why I wanted to throw it up this way. One is because I know people here are interested in variational problems, and I hoped I might spark some thinking like you're having. The other thing is that I don't know the answer to that at all. And I don't think anybody's really worked it out, because I don't think anyone has really thought about applying this point of view to this sort of situation. And I think it's a fascinating thing to possibly do. So I'm not sure, actually. It's one thing I've sort of been meaning to do for a while, is to take a typical problem and try to sort of work it out. But I don't know, maybe you guys know how you might do this.
The special point is that the observations which you are doing may be a result of some other critical point, if you look at, and what you see as a model is, and also going back to the issues of monsoon dynamics, of course, I don't understand much. There's a lot of instability, so is minimizer the correct thing to look at?
Yeah. Sorry, was that a question? I'm not sure. Was that just a statement? Yeah. Right. Okay. Yeah.
Any other questions?
So we should get into, I guess I should have done that, is maybe try to encourage a culture for the students asking questions and not being intimidated, right? I don't know if the students, if there are things that you don't understand, please ask, because you know there's this rule, right, that if you didn't get something, then there's something like a 70 or 80% probability that your colleagues also didn't get it. So you shouldn't sit there and feel like you have to suffer in not understanding. So, or you can ask me afterwards, or any of us.
So I guess one way we try to get over this problem would be to ask you, either volunteer, and if nobody volunteers, then force you to take notes, which is what I will start with in my tutorial in the afternoon, to make a list of students associate students to lecturers and for taking notes. So if you don't ask questions and don't understand, you won't be able to take notes properly. So at least the next lecture, this was an overview lecture, so we didn't really, and it will be, the PowerPoint will be available also, but starting in the afternoon, we will have proper notes being taken by students and so on. So we'll discuss that as we start the afternoon tutorial. So any questions for Chris right now?
Discussed two approaches to the problem.
Right.
How would one decide as to which is a more advantageous way to go about the whole issue? Which would be a better way to go about finding the answer? The conditional probability method or the optimization method?
I don't know that there's an easy answer to that. Right? That sort of depends which camp you come from, I think. I think what I can try to do is sort of explain it in a way culturally, right? That, this is, you can sort of see, right? This is sort of an applied mathematician's point of view, right? That you'd want to get the best estimate, right? And a probabilist point of view is to say there is no such thing as a best estimate. There's actually just a probability distribution function of estimates, right? So in a way, you come from different points of view. In terms of the sort of framework, what I wanted to get across was that those points of view actually correspond exactly. There's just sort of different ways of saying the same thing. So it's like there's that, what's it called, a Gestalt switch, right? Where you sort of, there's this picture you see where you look at it one way and it's the face of somebody, and another way it's two vases or something, or it's a vase, I don't know, it's two faces or a vase. So that's kind of one way to look at it. I think you'll see different methods during the next few weeks, the next 2 weeks and your 3 weeks, and you'll hopefully get to actually implement and use some of them. And you'll see that in a way, what I was saying here is that you are forced into the point of view of using Gaussians and using quadratic cost functions or linearizing, in which case the methods are actually, directly equivalent. So there really is technically no difference between the methods. But they generate different ways of looking at it, and the different ways of looking at it generate different ways of sort of solving it and different ways of approaching it, and which of those ways is better, I think, depends on the problem and depends also on what's been done before, because you don't want to reinvent the wheel. And when you're getting into large calculations that they're doing at operational weather centers, you can't show up at the Met Office in the UK or NCAR in the US and say, I think that you guys are looking at it all wrong, and you should be doing the Bayesian point of view, and you shouldn't be looking at it as a variational optimization problem or whatever. They'd say, but we've invested 20, 30 years in this. It'll take us 20, 30 years to get to the stage of doing it the other way, and so you just can't do that, right? So there's a lot of reality due to inertia too, which is a fact of life. It depends on the application, yeah. Depends on the
using tracking data.
So there, it has been used as just a computational tool, so that way it is purely mathematical. But when we want to get the picture of what is the whole thing, almost each book, it depends on the author's working knowledge.
Right.
So there are many books available describing the problem statistics point of view.
Right.
For mathematics, there are relatively less. To start with, everybody goes with the observation equation and more data, so we go for least squares method, and sequential least squares, we go for Kalman filter.
Right.
When it comes to looking at the whole picture,
right,
at least today how I have seen it, I have not seen in one book.
Right.
There are 2-3 books where it is given in a different way. Maybe someone has to give it the link.
Yeah, so actually a good answer. That's a good answer. It depends on the application and depends on the question you're asking. That's always.
Isn't it at the end like ensemble Kalman filter data assimilation also for that so because of that we will get a probabilistic forecast. So isn't that more appropriate for modern parallel computing algorithms? Also, we don't have to calculate the tangent linear model if to linearize this one.
That's right. That's right.
So it's more appropriate for like ensemble forecast. This ensemble data assimilation, like sequential data.
That's right. Yeah, I think that's right. Do you want to address that, Ahmed? Maybe he will answer that better than I will.
I mean, that's one of the reasons why the ensemble Kalman filter approach is very popular. But I guess one of the points which you were mentioning towards the end about non-linearity versus dimension, the ensemble Kalman filter does not really address the non-linearity issues comprehensively. So that's one of the.
I would like to point out that regarding ensemble and variational, like now 4D bar and ensemble Kalman filter, both are like parallelly being studied, and both are can be said as comparable computing. In two respects and also regarding atmospheric science or meteorological purpose, if we study the 4D bar in certain cases and ensemble Kalman filter in certain cases, and like competitors.
Yeah, that's right.
The jury is still out. There is I think ensemble Kalman filter versus 4D bar. Yeah. So there's a paper by Kalman titled ensemble Kalman filter versus 4D bar. Yeah. So and I don't think there's a definitive answer yet. If you're in Europe, it's 4D bar. If you're in US, it's Kalman filter.
So the words coming out about what I described as the variational method is known as 4D VAR, and and so 4D VAR versus the ensemble Kalman filter is a major sort of competition going on. Ensemble Kalman filter, how we see it, I think, in the US is that ensemble Kalman filter is very favored in academic circles because of this nice conceptual use of the nonlinear problem, and also because it's relatively easy to set up and to get going, whereas 4D VAR is not. It's sort of as some people say, well, if you've got 10 years to invest, then do 4D VAR, but otherwise do ensemble Kalman filter, because you can get ensemble Kalman filter going up for running for a new system in perhaps a matter of weeks, whereas it takes a long time to get 4D VAR really working. On the other hand, it's also true that I think almost every operational weather center in the world uses 4D VAR. I think that's also a true statement. So.
I think in the US they use this breed vector. Yeah, 3D vectors.
Yeah, I think actually the US is somewhat behind, in fact. So they used. I think they've been using.
But the basis on this bread vectors, purely.
Well, at NCAR, Jeff Anderson developed ensemble Kalman filter to a very effective degree, but he actually got the ocean and climate people at NCAR to use the ensemble Kalman filter, but the weather people will not use ensemble Kalman filter. No, not operationally at all.
So I guess we could continue our discussions over lunch now, and let's thank Chris again.